Hello friends, E076 here with the Pulling Your Homework Physics Series podcast. If you're looking to prepare, review, or gain an added edge or point of view about topics in physics, then look no further. Tune in each week to unlock your understanding of the physical world surrounding us. And now let's dive right in.
Alright friends, let me welcome you to the Halloween 2015 trilogy of podcasts from the Pulling Your Homework Physics Series podcast. I am your host, Eli Hibbett. Very glad to be here with you on a wonderful Halloween evening. And so, without further ado, let's dig in. So, there is a great live science article entitled The 9 Biggest Unsolved Mysteries in Physics. And so, for the last 3 episodes here, last 2, and then this one, we've been doing in chunks of 3. So if you haven't heard the first 2 parts of this, do go back and check them out. In part 1, we'll do numbers 9, 8, and 7. Last time we did 6, 5, and 4, and so now we're going to do the top 3 unsolved mysteries in physics. So very cool little series here. So let's hit up number 3. So far, my favorite ones have been 7 and 5. Number 7, why is there an arrow in time? And number 5 was, how come, why is there more matter than antimatter? Great question. So let's see if these ones will compare in any way. So number 3, how do measurements collapse quantum wave functions? In the strange realm of electrons, photons, and other fundamental particles, quantum mechanics is law. Particles don't behave like tiny balls, but rather like waves that are spread over a large area. Each particle is described by a wave function, or probability distribution, which tells what its location, velocity, and other properties are more likely to be, but not what those properties are. The particle actually has a range of values for all properties until you experimentally measure one of them. Its location, for example, at which point the particle's wave function collapses and it adopts just one location. But how and why does measuring a particle make its wave function collapse, producing a concrete reality that we perceive to exist? The issue, known as the measurement problem, may seem esoteric, but our understanding of what really is, or if it exists at all, hinges upon the answer. So, this is that. I mean, we talked about it a little bit here, but quantum mechanics. The whole idea of quantum mechanics is that everything has a wave function. Particles and an electron doesn't really orbit the atom. It doesn't just go around in a circle like a planet going around the sun. It actually is a superposition of states, and it just kind of pops all around. Its position changes, not discretely, but just kind of goes all over the place, and it forms what's known as like an electron cloud. And if you want to know where this electron is at any time, you can't just say, oh, it's in position X. It started in motion here, and it's going around in this orbit, and so it was, on this side before, and so we measured its velocity, and now it's on the other side, halfway around, and so we know exactly where it is. It doesn't really work that way. But what you do know is that, for an electron orbiting an atom, we know that it's, it can be in these specific positions, and the chances of it being in those positions are very high. And so it's actually defined by quantum mechanics to be in none of those states in any time. It's nowhere. But it has a probability of being, high probability of being here and a very low probability of being anywhere else. So, what we consider to be the orbit of the atom has a very high probability of being right there, but the position can actually be anywhere in the universe. But the probability of it being there is just very small, which is how tunneling kind of works. If you put I don't know how to say it without being really confusing. If you put an electron in an energy situation where it can't escape, it's called a quantum well, where you put potential energy and it's just sitting there and there's a voltage on either side, and so it can't escape because it's being held in this position. It'll get out. It just decides, you know what, I'm done with this. I don't like this. I'm leaving. And so it actually uses this probability of being able to exist anywhere to get out and escape the bounds of the potential well. And so the question is, when we measure things, when we measure the position, when we observe it, we collapse the quantum wave function, and the probability becomes 100% that it is in a single location, even though before it was everywhere. And how does measurement collapse the quantum wave function? How does it become a reality? And what is so special about measuring? If you're just existing and the particle is in its wave function state where it can be anywhere at once, how does it know what a measurement is to collapse down? And so nobody knows the answer to this. Quantum mechanics is actually a very, very, very new field, and we're still trying to understand it and how wave functions work, but they work incredibly well. And so people know that they're real, and there's a wave-particle duality, and there's a problem where you send out two particles with entangled wave functions in different directions, and if you collapse one, the other one collapses. The other one has to change opposite at the exact same time, and so information is being relayed that's traveling faster than light, and it's a big problem because it violates a lot of laws of physics. But to make a long story short, too late. That's question number 3. How do measurements collapse quantum wave functions? Good question. I'm not really sure. I kind of lean to the fact that, even though we're sentient beings, there's nothing that special about us necessarily. And so the answers of physics are all still there, and that there's nothing that we know to be a measurement that makes it dependent to collapse the wave functions. So we can figure this out, but a lot of people don't agree with that. So anyway, let's go to question number 2. Oh, good question. Is string theory correct? When physicists assume all the elementary particles are actually one-dimensional loops or strings, each of which vibrates at a different frequency, physics gets much easier. String theory allows physicists to reconcile the laws governing particles, called quantum mechanics, with laws governing space-time, called general relativity, and to unify the 4 fundamental forces of nature into a single framework. But the problem is, string theory can only work in a universe with 10 or 11 dimensions, 3 spatial ones, 6 or 7 compacted spatial ones, and a time dimension. The compacted spatial dimensions, as well as the vibrating strings themselves, are about 1/billionth of a trillionth of the size of an atomic nucleus. There is no conceivable way to detect anything that small, so there's no known way to experimentally validate or invalidate string theory. That is the big problem. Even if string theory is correct, we have no idea how to figure out, to prove it. And so right now, it's still in the situation where it's just kind of a nice theory. And we have, what they do is, we've gone through dimensions. We know our 3D Cartesian coordinate system. We have our vertical axis, our horizontal axis, and our depth axis. And so we have X, Y, and Z, and they expand, they go on forever in their respective directions. And so imagine if we had a couple more axes there, right? Just throw a couple more arrows pointing out in all directions. Now, what they do is they take those axes, and instead of letting the arrow point out forever, they curl it up into a circle, and it's very, very small. It's not a big loop that you'd be able to measure, but instead that dimension is about 1/billionth of a trillionth of the size of an atomic nucleus. So those dimensions become very small, and that's kind of, in my perception of string theory, where the strings kind of hang out. And so the question is, okay, great, let's just say we're buying it, right? How can we validate whether or not this is true? It's a big problem. Because 1/billionth of a trillionth of the size of an atomic nucleus. We're talking about things that are so small. Well, let's get even deeper. We have Planck length, which is much bigger than the 1/billionth of a trillionth of the size of an atomic nucleus, and it's proven that we are not able to measure anything smaller than that. So there's no way, if quantum mechanics is correct, to detect these curled up, very small dimensions. And so it's a problem. And that is why we are going to start diving into Physics Fridays with first the fabric of the cosmos and then the elegant universe. The elegant universe is, there's a really good story about the elegant universe. So Brian Greene wrote the elegant universe. Great story, great book about string theory, which I have not finished. And he wrote it and dedicated it to his mother. And he asked her if she read it, and she said no. And he said, why? And she said, it's too confusing. I don't understand it. And so he wrote The Fabric of the Cosmos, his, not sequel, but follow-up book, to try to simplify it even more and make a book that even his mother would enjoy reading and understand. So we're going to start there, and we're going to go into Elegant Universe and try to see if we can figure out if string theory is correct. Maybe we'll light the fire in someone to who will actually solve that problem. I mean, there's a hope. That would be fantastic, and I'd be really excited about that. So there we go. Question number 2, is string theory correct? And yeah, that's a burning one. If we could say that string theory is correct, man, that would solve a lot of problems. And relativity and quantum mechanics would be unified, and we could all go home. So, but that is only number 2 on the list. What is number 1? I actually don't remember. Let's click over. All right, question number 1. Is there order in chaos? Physicists can't exactly solve the set of equations that describes the behavior of fluids, from water to air to all other liquids and gases. In fact, it isn't known whether a general solution to the so-called Navier-Stokes equations even exists, or if there is a solution, whether it describes fluids everywhere or contains inherently unknowable points called singularities. As a consequence, the nature of chaos is not well understood. Physicists and mathematicians wonder, is the weather merely difficult to predict or inherently unpredictable? Does turbulence transcend mathematical description, or does it all make sense when you tackle it with the right math? I don't know if that's true. Is that the number 1 unsolved mystery in physics? I guess it is. I guess that is the question, because if there are systems that we know are chaotic or described by chaos equations, and if they're not solvable, it's over. I mean, physics doesn't really do anything. I mean, we have certain situations where we can do basic calculations, but that would mean that, overall, I mean, even something as simple, quote unquote, as like a weather storm is unsolvable. It's not solvable. It's not like if we just had a computer strong enough, we could predict the whole thing. It is inherently an unsolvable system. It's so crazy that there is no way to predict what's going to happen. There's no set of initial conditions where we can set the wheels in motion and allow it to follow out in a predictable way. And so I guess that's the question, is there order in chaos? I guess, you know what, now that I think about it, it's kind of a big deal. Because if the answer is no, if there is no order in chaos, then science can only take you so far. And there is a limit to what science can do. So, yeah, that's a good question, and apparently we don't know the answer to that question. And there are a lot of very complex systems. And actually, when you think about like what's going on in our world, they're not very complex. They're things like weather. I mean, when you look at the universe, you see these monster structures like these galaxies, and this, weather that's going around us is only a very small part of a very small planet in a very tiny part of a galaxy. So if we can't even predict that, I mean, what luck do we have trying to do the rest of the universe? And we would have to abandon science. So we need an answer to that one right quick, guys. If you guys could get on that next generation of physicists and answer that one, that would make everybody's lives a lot easier. But there we go. That is are the 9 burning biggest unsolved mysteries in physics according to livescience.com. So there we go. Happy Halloween, guys. That's going to do it. So take care, and I'll catch you next week. Stay frosty, stay in the zone, and I'll catch you next time, guys. Take care. Happy Halloween.